So today we're going to be talking about Wiggers diagram. Wiggers diagram is basically a comparison between EKG volume and pressure. It's actually going to be used to prove that the EKG is showing depolarization, and from that depolarization, our muscle is actually contracting. Our heart is contracting and causing a volume change and pressure changes within our heart. So let's go ahead and start breaking down this diagram. So when we read this diagram, we want to start all the way from the left and read left to right. So the first thing that should be coming across your screen is going to be the EKG portion, which I have labeled. So right now we're going to start with the P wave of the EKG. The P wave of the EKG is going to be our depolarization of our atria. So the SA node fires. It's going to send signal through the atria, through the gap junctions, everything like that. And depolarization, as we know it, is when it causes the atrium to contract. So immediately following this depolarization, we see a subtle pressure change in the left ventricle, and that's because the left atrium is contracting, which is going to be active filling for the left ventricle. And right after you see this pressure to start changing, you see a slight volume increase in the left ventricle as well. Passive filling only accounts for about 20% of the blood that goes into the heart, because the majority of it goes into the left ventricle by passive filling. So that is our first portion here. We're going to move on. Right now we're going to move on to our QRS complex and our isovolumetric contraction. So our QRS complex is going to be where we have the ventricle depolarizing, and immediately following the depolarization, like I said before, we're going to have contraction. So during this contraction, QRS happens, and immediately you see this highlighted portion where the pressure is increasing in the left ventricle. I want you to notice, though, you look at the volume right under this spike in pressure. You do not see the volume decreasing or increasing in the left ventricle. And that's because the muscle is starting to contract, so it's putting pressure on the left ventricle. But we're not actually ejecting any blood out of the ventricle yet, because we have to first overcome afterload, because there is, again, back pressure from the aorta. The blood that's in the aorta is putting pressure, back pressure. And in order to actually eject the blood from the left ventricle, we have to overcome that afterload pressure. All right, now we're going to move into the next section. I've labeled it here. There's a little green dot, and I labeled that number 1. That is where we are actually going to exceed that afterload. That is where the aortic valve is going to open. And right after it opens, I want you to look down at the pressure, and you see an immediately large drop in volume. And it's because that pressure is overcome, and now we can shoot blood out of the heart, out of the aortic valve. This is actually what's proving that the contraction is taking place, because immediately following that depolarization, we have an increase in pressure. And our pressure is increasing, but our volume is not, and that can only be because our heart is contracting. So right after that pressure drops in the aorta, in the ventricle, we're going to have the T wave, and the T wave is going to be where our diastole is taking place for our ventricle. And I have labeled it, we'll discuss it on the next slide, but you can see I drew a flat line right under there. And we'll talk about that in just a second. All right, so here we're going to start talking about, first I'm going to start with that flat line. That flat line is there because if you look up top where number 2 is, there's a huge drop in pressure, and is also labeled where the aortic valve is going to close. And if the aortic valve is closed, then there's no blood that is leaving the heart anymore. There's no blood leaving the ventricle, and we have not yet started on our filling process from the atrium into the ventricle. So that's completely flatlined. Our volume is flatlined because we're not changing. And there's really no blood left in that ventricle. So it's not changing anymore. There's no more contraction happening because is after the T wave, so the left ventricle is no longer contracting. All right, and now I want to shout out this yellow highlighted line here. Now we're starting to see the volume increase in the left ventricle, but we're not really seeing the pressure increase, and that's because there is no ventricle contraction happening here. And that is because that is the passive filling from the left atrium down into the left ventricle. And now more, I want to look up here on this highlighted spot that's purple. This highlighted spot is purple. It's right where we're looking at that. That is the aortic pressure. And that is going to be happening. That is going to increase some because we're going to have back pressure on the aortic valve. And then slowly we're going to look at the pressure in the aorta slowly tank off. And that's because there's no more blood being ejected into the aorta, but we are pumping it through our body. So it's going out into the system and it's going to wait. It's going to go back up once the ventricle contracts again and pushes blood back into the aorta. All right, now we're going to dive into some atherosclerosis. Atherosclerosis is going to be the buildup of plaques in the artery walls. It's not going to be on the inside of the lumen. It is actually going to be just underneath that first layer of that artery wall. And this is going to cause the narrowing of our blood vessels. And I've put a little picture up here for us to see that the buildup of plaque under that wall. You can clearly see the lining. It's under the lining and it's causing an obstruction of blood cells to be able to flow. All right, now we're going to dive into the pathophysiology of what atherosclerosis is. Atherosclerosis starts out by being caused by the buildup of fat and cholesterol under that initial lining of the artery wall. So first I want to give you a little background. There's this thing called low-density lipoprotein, or LDL. You may have heard of it as being called the bad cholesterol. It is only bad cholesterol in quotation marks because you do need LDL because it transports fats and cholesterol around your body, and you absolutely need those. Otherwise, you can't really burn fat and cause muscle contraction or have energy of any kind. So we do need them, but the buildup of them is very dangerous because it gets under the lumen. And I'm going to talk to you first about the two different types of LDL here. There is large LDL and then there is small LDL. Against common belief, I initially thought that large LDL would be the bad type of LDL, but it's actually the small LDL, and here's why. I drew this picture here of, this is a blood vessel right here, the little hoops, and there's gaps in between them. And these gaps are going to allow this small LDL to actually seep through them. And now that small LDL is stuck under the lumen and not where it should be. It should be in the lumen, but now it's stuck underneath it inside the artery wall. And now we're going to talk about more of the steps of how atherosclerosis is formed. So when you have your blood vessels, you have branching that occurs and you have something called a bifurcation point. And I drew this here so we have a straight line and then we have branches occur. And at that point, that is going to be called the bifurcation point. And when that branch happens, you're going to have those blood vessels that are those blood cells that are going to bang against that wall. And that is going to cause inflammation and physical damage to that artery wall. So that's going to be the first step in causing this atherosclerosis, is that physical damage to the artery wall. And then the next step, whenever we have physical damage, we know that inflammation is going to occur. And it's going to send alert to the rest of the body that we need our first responders. We're going to need our white blood cells that are in charge of being on that scene first and taking care of whatever inflammation is going on there. So step 3, the macrophage is coming to the rescue. Macrophage is a type of white blood cell, and its main goal is to eat and engulf and oxidize whatever it consumes. So if it's a foreigner, it's going to eat, engulf, oxidize it because it does not need to be there. So these macrophages are hungry for SDL, the small LDL. So when it gets to this space of inflammation, these macrophages are then also going to slip through these gaps. And it's going to see that LDL there, and LDL underneath the lumen is a foreign substance. It sees that the LDL should not be there. So this macrophage is absolutely functioning the way it's supposed to be. It is supposed to engulf foreigners. But LDL is not supposed to be there. It's underneath the lumen. So it decides that it's going to eat and engulf the LDL. And once it eats and engulfs this LDL, it's going to form something called a foam cell. And these foam cells are going to gradually build up and build up because you're going to have more LDL slip under, more macrophages that are going to eat and engulf over time and over time. That's going to happen because that inflammation from that physical damage in that artery is going to happen more and more. And when you have more of this small LDL in your bloodstream, there's more and more that can slip under the lumen. And then this cycle just happens over and over again. And gradually, it's going to narrow your blood vessel even more. So as you can see here, I drew two different blood vessels to compare. So we see the healthy blood vessel, there's no buildup, but under this is going to be the atherosclerosis. So now you can see that what happens when you have this buildup of tons of foam cells underneath the epithelial lining. And that's going to cause the narrowing of the blood vessel, and then not as much blood can flow through because you don't have as much space. And what we know about when you have a smaller space is you're going to increase your blood pressure, which leads us into the next part. How does atherosclerosis affect the Wiggers diagram? So we already talked about what normally happens. We normally have this afterload that has to be overcame by the pressure in the left ventricle. Once that depolarization happens of that left ventricle, it starts contracting. We see the increase of pressure in the left ventricle. And we have to overcome the afterload in order to actually inject the blood. Well, if this atherosclerosis is in our aorta, it's going to end up causing the pressure in the aorta to increase, which means that the time and amount of force that it takes to overcome this afterload is going to be more. Now, how is that going to affect the Wiggers diagram? Well, I drew this little dot here, this yellow dot, and say let's shift the time the aortic valve opens now over to the right. So that's going to change the time that the valve opens, and it's then going to, if you see, it's going to shorten the amount of time that we have to eject blood out of the heart. Because what's not changing? The firing of the neurons, the depolarization and repolarization, none of that is changing. Only the mechanical system is changing. So if we have to have more pressure, more time to overcome the afterload, less blood is going to be ejected. So, like I said, it depends on where this atherosclerosis is located, because you can have the atherosclerosis in the aorta, which is then, like I said, it's going to increase the afterload and decrease the ejection time, which means less blood is going to be able to be ejected. We're getting less oxygen to our bodies, less blood to our bodies, and that causes issues. As well as if atherosclerosis could also be within the heart muscle arteries. How is that going to affect it? Well, it's not going to so much affect the preload or the afterload portion, but it will affect how much the heart can actually contract itself. Because what does our heart need in order to contract? It needs oxygen. And what does blood carry? It carries oxygen. Well, if we have less blood getting through our cells and being able to be administered into our heart muscle, we can no longer contract our heart as much, which means that we're going to have decreased ventricular inotropy. And decreased ventricular inotropy also is going to just cause us to have, both of these actually are going to cause us to have increased preload, but not the good kind of increased preload. Because over time, it's going to cause a lot of issues of, it's going to stretch out our heart. It's going to cause us to potentially develop cardiomyopathy, which is a loose heart because it's being overstretched. And over time, we're just going to have a lot of preload and not a lot of blood getting actually out into our bodies. And of course, this isn't necessarily the Wiggers diagram, but atherosclerosis, if it were causing a blockage, then it's going to cause us to potentially even have a heart attack if we get a complete blockage. And then if we have a heart attack, then that's going to cause us to get even less oxygen to our heart. We're going to have cardiac cell death, which is then going to lead us into having less ventricular inotropy and less blood getting to our bodies. And over time, that just causes a big issue. So, yeah.